and welcome to lecture number 3. And what we're going to do now is we're going to finish chapter 1 and move on to chapter 2. So we are on slide 13, and it says example, and hopefully you all have access to it. Is anyone still having issues downloading or viewing the PowerPoint off of Canvas? I know I got an email from someone. That's just a strange hand coming out of nowhere, but I got an email from someone who is still having issues. I don't know if it's this class or the other class. So are there any questions, anyone, on getting access to the PowerPoints? Okay, so then I'm not going to share my screen. I'd rather see your faces and see whether or not, I get that face of confusion or that face of understanding, which I don't get when I'm sharing. So let's look at slide 13. It says complete the sample space below for the situation of tossing 2 fair dice. And you'll notice if you look at this box, how many squares are there in the box?
36.
There's 36 of them. And so they're giving us a spoiler. They're basically telling us that there are 36 outcomes. Now let's see what they are. And you should write them out because we're going to need them to answer these questions. The first box, the top.
Wait, Professor?
Yeah.
Are you sharing your screen?
No.
Oh, okay. I was lost.
No. You should have the PowerPoints from Canvas. You can download them. They're PDFs. You should have no problem accessing them. So on slide 13, the top left says 1, 1. What is the physical connotation of the numbers 1, 1? What is happening in context? What's really going on here when you roll 2 dice? If I say the outcome is 1, 1, what does that mean?
You're getting 1 on each die.
I'm getting 1 on each die. The first die is a 1, the second die is a 1. When I have 1, 2, what does that mean?
One dice is 1, the other dice is 2.
But you got to be more specific than that. The first die says 1, the second die says 2.
Okay.
Because if you just say 1 die says 1 and 1 die says 2, then 1, 2, and 2, 1 are really the same.
Oh, yeah.
But they're not. 1, 1, and 2, 1 are different. So anyways, what should be next in that first row?
2 and 1.
No, in the first row, what should be next?
3. Oh.
1, 3. Yeah, go ahead, Miriam. Your hand was up. Were you answering a question or do you have a question? You're on silence. I can't hear you.
It's 1, 3.
Oh, it is 1, 3. Okay. And then next is
1, 4.
1, 4, 1, 5, 1, 6. That's it. So fill out the entire table. Okay, it should take you 30 seconds to write it out, but we're going to need this to answer the questions. So after, and I'll do it here. I'm not sure if you can, how well you can see my board, but what's the point of having a whiteboard if I'm not going to use the whiteboard, right? So your box should have a total of 36 possible outcomes that are structured by what you get on the first die and what you get on the second die, correct?
Yes.
Okay, so let's look at the questions. First, are the 36 outcomes equally likely?
Yes.
Yes, they are, right? There's no reason why a die should show one number more likely than any other number. They are equally likely. We love sample spaces of equally likely outcomes because the math that comes along with them is a lot easier. We're going to have situations in this course where they're not going to be equally likely outcomes, and it's just harder math. So next question, what is the probability of rolling doubles?
Would that be
6/36.
6 out of 36, right? You look through all 36 possibilities and you ask yourself, of these 36 possibilities, how many of them are rolling doubles? And the answer is the main diagonal. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Then the question is, find the probability of rolling a sum of 7 or a sum of 11. Again, I'm not looking for two answers here. There's one answer. And the question is, what is the likelihood of rolling a 7 or 11? So what you're going to do is you're going to calculate. You're going to count how many of these 36 outcomes give me a 7 or an 11. And what's the answer?
8/36.
8/36. 8 of these outcomes give me a 7 or an 11. The 7s are along this diagonal, I think, right? Going that way. And then 11, there's 2 in the bottom. I didn't get that far when I did it on the board, but you should have gotten that far. 5, 6, and 6, 5 add to 11. Correct? Now, anyone know a game in life where rolling a 7 or an 11 might be important? Any degenerate gamblers here?
Isn't it?
Anyone know?
I forgot.
Poker.
It's not poker.
I have no idea.
21?
You don't roll dice in poker. What are you talking about? It is craps. Anyone here play craps or ever heard of craps? Good. Don't do what I did and lose all your money. It's not good. Okay. So never go to Vegas. You're gonna lose everything. Anyways, so next question. Now, top of the next slide, slide 14. It says to construct a probability distribution table for the sum of two dice. Now, usually when you roll two dice, what you care about is the sum. So let's remind ourselves what a probability distribution table is. On the left is a column of all possible outcomes, and on the right is their corresponding probabilities. So when you roll two dice, if you care about the sum, what is the smallest number that you might get?
2.
2. The first number in my left column is going to be a 2. What's the next number that I might get when I roll two dice if I care about the sum?
3.
3. And then what comes next?
4.
4. And up until what number? What's the highest you can possibly get when you roll two dice if you care about the sum? 12. So the first column is going to be 2 through 12. You can't roll a 1 with two dice. It makes no sense unless you're cheating. Like, I'll put a die with nothing on it. That'll be 0. It doesn't make sense that way. People will know you're cheating right away. Don't try that either. So 2 through 12. And then what we need to do next in the next column is a little more challenging. What we have to do in the next column is we got to calculate the probability of all of those answers, all of those possible numbers. So let's start with 2. What is based upon your square table that you should have still on the previous slide, what is the probability of rolling a 2?
1 out of 36?
1 out of 36, because out of the 36 possible equally likely outcomes, only one of them gives you a 2.
Total of
Snake
2.
eye. Huh?
You said a total. You're looking for the total,
A
right?
total of 2. So 1, 1 is the only way to get a total of 2, correct? No other way to add up to 2, right? Just a 1 and a 1. So out of the 36 outcomes, only one of them gives you a 2, so the probability is 1 over 36. How many ways are there of getting of rolling a 3?
2 out of 36.
It's going to be 2 out of 36 because it's 1, 2, and 2, 1. So the probability of rolling a 3 is 2 out of 36. It's a little more likely. How about a 4?
Are you doing this on the probability distribution table?
So yeah, we're writing out the probability distribution table, but we're getting our answers from our square that we had in the previous slide.
Right, but the top of the columns are the number of,
So yeah, the top column, I would write it like this: X and P of X. X could be 2 with probability 1 out of 36. X can be 3 with probability 2 out of 36. And that would complete the table. So what's the next possible value for X? It's 4. And how likely is it that we can get a 4?
3
How
out
many-
of 36.
3 out of
3 out of
36. Right? 1, 3, 3, 1, or 2, 2. And then we go down the table and we fill it out. Now, do you see a pattern forming in your square that can help us just do this quickly?
Diagonally.
Diagonals, right? 1 and 2, 3, 4, 5, 6, 7, 6, 8, 9, 10, 11, 12. Right? So we should be able to fill this out very quickly. What's the most likely outcome, by the way?
7.
7. 7 is the most likely outcome. It has the highest probability of occurring, which is 6 out of 36. No other number is as likely as that. So in the bottom of slide 14, when it says what is the most likely sum, the answer is the most likely sum is 7. Does that make sense for that problem? Okay. Now, I just want to make sure we're all caught up because the next part, my class yesterday, they had some difficulty with, so I want to go a little slower, try it a slightly different way. But they were having difficulty with it, so I want to make sure that we're all ready for it before I move on. Okay, 1 second. I have a student trying to get in who has the wrong link. Give me a second. I'll let you guys catch up a second while I figure this out. So just take a minute.
So just so I understand, the probability distribution table only goes up to 6, right? 2, 3, 4, 5.
Oh, 1 second. 1 second. Give me 1 second. I'm trying to. I want to make sure the student gets in, so give me a second, please. I don't see an email on this one. I don't see an email. Madison Kersner, are you here? No, Madison Kersner. Okay, give me a second, guys. Someone who's supposed to be here is not. She's having difficulty getting in, so I want to make sure that she's going to get into my class. Just give me a second. Just relax for a minute. Gmail. Okay, hold on. Okay. Oh, 6:30 to 8:10. Oh. Not even in this class. That's crazy. Okay. All right. So we're back. So let's take a look. Okay. So let's go to the next question. So someone had a question. I'm sorry.
I just want to make sure the probability distribution table only goes up to 6, right? 2,
No.
3, 4, 5, 6.
No, 7, 8, 9, 10, 11, 12. Any possibility. It goes all the way to 12, right? When you're adding 2 dice, it could be a 2, it could be a 3, it could be a 4,
okay.
5, a 6,
Sorry.
7, 8, 9, 10, 11, or 12, right?
Yeah.
Because any of them are possible, they're all included.
Got it.
Okay?
Thank you.
Okay. So where is the power? Oh, here we go. Okay. So now we have a different situation entirely. We're still rolling 2 dice, but we're playing a different game. Okay. This is on 14 top right. Okay. We're still rolling 2 dice, but we're playing a different game. And the game is as follows. I care not about the sum. I care about whatever the larger number is. So if you roll a 1 and a 3, then what do I say you got? A 3. It's the larger number. If you roll a 2 and a 5, then what do I say you got? A 5. It's the larger number. What if you roll doubles, a 3 and a 3? What do I say you got? Well, the prompt specifically says, it says if the number's the same, just call that the larger number. Okay, that's what the question says. So if you roll a 3 and a 3, the larger number is 3. Okay, so we're going to construct a probability distribution table for this new game that we have. Let's start, well, again, the first thing we got to do is we have to list all possible outcomes. Okay, so the first one, what is the smallest possible outcome that we might get if what we care about is the largest possible number?
1.
1. What is the next one that might be the largest possible number if we roll 2 dice? 2.
2.
And up until what? What's the largest number of largest possible numbers is 6. So the first column of our distribution table is going to be 1, 2, 3, 4, 5, and 6. Those are the 6 possible outcomes for what we care about is the largest possible number. Does that make sense? Okay. So how many ways can the largest possible number be 1?
1 out of 36.
Good. 1 out of 36.
Can you ask that question again? How many ways?
How many ways can the largest possible number be 1?
1 out of 36, you said. 1 out of 36?
1 out of 36.
So that goes next to the 1.
That goes next to the 1. How many ways is 2 possibly the largest number?
2 out of 36.
What are the 2? And by the way, that's not correct. It's 3, but because I saw someone hand up with 3 and she looked a little confused. It is 3, but if you say 2, I'm just curious, what are the 2 that you're thinking of?
I was thinking 1, 2, and then 2, 2, since they're the same.
What about 2? What about 2, 1?
I said 1, 2.
What about 2, 1? 1,
Oh,
2,
okay.
1, 2, and 2, 1
I
are different scenarios,
Yeah, I see.
right? So 1, 2, 2, 1, and 2, 2. Those are 3 ways where the largest number is 2.
So 3 out of 36.
So 3 out of 36. So go ahead and fill out the table.
Are you showing how you're going to draw out the table, or do we just like?
Well, I want you to see if you can find a pattern.
Would it start looking like a backwards L almost?
Yes, it would.
Okay.
Excellent. So this is something that we do in math. We look for patterns. Okay, we look for patterns to save us time and energy and work. Does that make sense what I'm saying? Okay.
Are you looking at a pattern on the chart, the 6
On the-
spaces?
In the box of 36, that's exactly what you're doing. You're trying to come up with a pattern. That's right. That's exactly what you're doing. Does that make sense so far? Okay.
Yeah.
So the next line, it says, so did you guys all finish the table? So what is the least likely number?
1.
1, because there's only one way that it could be 1, right? So when you make probability distribution tables, just be aware every scenario can have a different table depending on what it is that you're after. Okay, just because you rolled 2 dice doesn't mean that we're all going to have the same idea with what the table is, right? It depends on what you're after. Do you care about the sum? Do you care about the larger? Do you care about the smaller? Do you care about the difference? Do you care about the product? What do you care about? Whatever it is that you care about, the left column are all possible values, and the right column are how many ways it can possibly happen. Does that make sense? Okay. So this takes us to the end of the first chapter. Let's take a 5-minute break, and then we'll jump. And I already posted the second PDF, so we'll take a 5-minute break, and then we'll jump into the second PDF when we get back. Okay? So at about 2:48 on my screen. Okay, I'll see you guys in a few minutes.
Professor, I don't know if I can ask you a question now or after class, but
Go ahead.
I tried the permission number that you had given me, and it's still not letting me enroll. It's
Wait.
like
The permission number that I gave you, I thought was to this meeting.
Oh, okay.
I wasn't giving you a permission number to the course. I can't do that. I have to pass you along to the math department, and they will do it.
Okay, perfect.
I thought you were trying to add this meeting, so I gave you the permission number for the meeting. Now
Okay.
I see why it didn't work.
Yeah, okay, thank you. So I'll just expect an email from the permission number just to add, or how does that
So
work?
yeah, so what I'm gonna do, so do me a favor. You have my email. I don't know if you ever included your ID number.
Yes,
So
I did.
You did. Okay, so what I'll do is I will pass that ID number and your name on, and the math course, of course, on to the math department. And they should approve it because you're in a class already. So it's not like, hey, is she eligible? Obviously you're eligible because you're here. Okay, but I can't do it myself. I have to ask them to do it, and I will explain your situation, and hopefully they'll say okay.
Okay, perfect. Thank you so much.
You're welcome. Okay, so let me load up. It's about time. Let me load up the second PDF. Let's give everyone just another minute to get back. Hopefully they'll be back soon. Yes, question? Wendy, your hand was up or no? Or you just, saying,
No, sorry.
we're just saying I'm number one? I get it. I get that a lot.
Professor, the
Yes,
second lecture slides are in the Files tab, correct, on Canvas?
yes. I'm putting them all on files. Correct.
Okay, thank you.
Trying to be preemptive and getting them before we need them as opposed to 3 days later. So, I'm working on myself. My girlfriend will be so proud. So, no, I'm not just kidding. I'm not really working on myself. I'm happy the way I am. Okay, so homework number 2. Homework number 2. Not homework number 2, I'm sorry. Chapter number 2, simulation. So, thank you. So what is a simulation, right? A simulation is essentially doing one thing to mimic the results of something else. For example, let me give you a straightforward example. Suppose you roll a die, and I ask you, what is the probability of getting an even number on rolling a die? What would you say? You roll one die, what is the probability of rolling an even number?
3 out of 6, yeah.
3 out of 6, which is 1 out of 2, 50%, correct? And let's say it's imperative that you roll the die right now. We need to know, did you get an evens or did you get an odds? It's life can't go on without this information. But there's only one problem. You don't have a die. All you have is a coin. So I can simulate having a die by flipping the coin, saying heads is evens, tails is odds. It's still 50-50. And essentially, I did the same thing, right? I did something with a 50-50 chance. If it's heads, I say I got an evens. If it's tails, I got an odds. And I did one thing by mimicking something else. Does that make sense?
Yes.
This is what simulations are. Simulations are when you do one thing to mimic the outcome of something else. Because sometimes you just don't have it, you don't have it in front of you. Okay, or it's too difficult. Or it takes too much time, or it takes too much money, or it takes too much energy, whatever the case may be. There are situations when what you do is one thing to simulate or to mimic something else. So in this example on the first slide, what do we see? It says simulation is a method of estimating a probability empirically by using a device that generates outcomes with the same probabilities as the actual chance situation. Whatever the actual situation that you want to do, you simulate it by using something else that has the same chance. In elementary school, simulation is done using physical objects that kids are familiar with: dice, coins, spinners, cards. In this class, when I ask for an example of a probability of something, just use one of those 4. Don't come up with some really complicated scenario like, oh, yeah, well, the Super Bowl, or, this or that. Well, Super Bowl, which teams are playing? Who has home field advantage? What are their records? Is anyone injured? I mean, it's such a complicated scenario. Don't go there. Just use simple objects that children and even adults can understand well. Now, when I was a kid, we played cards a lot. We didn't have the internet. We didn't have smartphones. We didn't have this proliferation of computers like you have today. So when we were bored, we just sat around and we played cards. So we all knew how many cards there are in a deck and how many suits and how many denominations. We all knew that. But sometimes when I teach classes, people don't know that. They have no idea, some people, what cards are. Thank you. They have no idea what a card is or what cards are, how many cards there are, nothing. So before I use this as an example, I have to ask this class, is there anyone here And it's okay if the answer is yes, but is there anyone here who just is not familiar with a deck of cards?
You asked this question last class too.
Did I?
Yes.
Well,
First day.
We are your one smart class that knows what a deck of cards is.
great. Well, that was a waste of time. Okay, so anyway, so let's move on to the second slide. It says example. According to the High School Youth Risk Behavior Survey, 1/3 of Los Angeles Unified School District high school students report that they have tried cigarette smoking. How can you model the situation of picking 12 students at random and counting the number who have tried cigarette smoking? So in other words, a survey came out that says 1 in 3 LAUSD high school students has smoked before. And I'm like, you know what? I'm going to go hunt down 12 kids and ask them whether or not they've done smoking. There's one problem. I'm scared of those kids. Okay? I don't want to talk to them. I don't want to be anywhere near them. So how can I simulate this situation without actually dealing with these students? I need something that has the same chance of occurrence as the LAUSD situation, which is 1 in 3. So I need something that I can use, something simple, dice, cards, coins, spinners, where I can create a scenario where something has a 1 in 3 chance of occurring. Can I do that with a die? If I have one die, can I create a scenario where something has a 1 in 3 chance of occurring? What would that be? What scenario for rolling a single die would I say the probability of this occurring is 1 out of 3?
Rolling, seeing if you get even or odds as a yes or no.
But there's a problem with even or odd. That's not 1 in 3. Even and odds is 1 out of 2. It's 50%. I need something 1 out of 3.
So you have to roll.
Would you be able to do like 1 and 2 and 3 and 4 and 5 and 6
So
together?
1 and 2 and 3 and 4 and 5 and 6. Can you?
Well, I mean,
Can you say that
I
again
mean, like
with
if you yes, if you roll 1 and 2, it could mean that they do. 3 and 4 can mean that they don't, and then 5 and 6 that they don't.
Okay, so then 1 and 2, 1 and 2 that they
choice.
smoke, and 3, 4, 5, 6 that they don't. Right? 1, 2 smoke, 3, 4, 5, 6 don't smoke.
Or even and odd numbers?
No, even and odd does not work. Even and odd is not 1 and 3. Even and odd is 50-50.
Oh, you need something where there's
I need
3.
something where it's 1 and 3.
1
So
out of 3.
So what is the probability of rolling either a 1 or a 2?
1/3.
1/3. That's what I'm looking for.
Yeah. Okay.
So if I say, okay, if I roll a 1 or a 2, we'll call that a smoker. And if you roll a 3, 4, 5, or 6, we'll call it a non-smoker. Then I can roll this die 12 times, and I count how many 1s and 2s that I got. Each one of them was a smoker, and I have my answer how many smokers there were. I didn't actually talk to them. I didn't actually go out and find them. I did a simulation, which is taking the place of actually doing all that work. Does that make sense? Students yesterday were having a big problem with simulation, so it's okay if you guys do too. I tried changing things a little bit because, you know, as a teacher myself, I'm also learning. One thing does not work, try something else. I'm evolving just like you guys are.
So we're not trying to use mathematics, like for instance, when you said 1 in 3, but we're choosing 4 students, my mind went to get the denominator 12 because that's your total, and then whatever you multiply with.
So it's not like that. What's happening is as follows. Can you guys all see the board well enough? So we have the following situation. We're going to take a die, and we're going to actually take 12 dice. And we're going to roll 12 dice, or the same die 12 times. It does not matter, as long as you get 12 outcomes. And we're going to say that if die number one, if it's a 1 or a 2, that's a smoker. And if it's a 3 through a 6, that's a non-smoker. So if the first die rolls 1 or 2, the first die represents a kid who smokes. And if the first die is 3 through 6, the first die represents a kid who does not smoke. Every die will either be smoker or non-smoker. So I'm going to have 12 different outcomes at the end of this. Every die is an outcome. So I might have at the end maybe 5 smokers and 7 non-smokers. And my result will be, this is just an example. This is an example. And my result will be, oh, yeah, I went out and I talked to 12 students and 5 of them were smokers. Did I actually do that? No, but I simulated doing it. I did something that has the same chance of occurring as that without actually doing it. Because you know what? How much time does it take out to actually go and find 12 students randomly and ask them this question?
A lot of time.
A lot of time, correct? It's a lot easier. 12 dice takes 2 minutes.
Why did you choose 1 and 2? Is that because it's a third of the 6?
Yes.
Size of the dice. Okay.
Yeah. Exactly. Does that make sense?
It does now. Yes. Thank you.
Okay. So let's move on now. Okay, so we simulated it with a die. How can I simulate the same situation with a spinner? Remember, you're creating a spinner.
You'd have to put like 1, a 2, and a 3, right? And then every time you spin it, if it lands on 1. Or...
Beautiful, but you got to give me a little more information.
I thought you were interested just in the number.
Sure. Well, here, ready? I'm going to do what you just said. Ready? Here's my spinner.
Divided in 3 parts, right?
Okay, but that's divided into 3 parts.
No, but 3 equal parts?
Okay, so that's what I was asking for. When I say give me more information.
That's what I was picturing in my head, but I didn't verbalize that.
So just remember, we're all trained to be teachers here, correct? And again, it's the same thing for me. Sometimes I'm thinking one thing, I say one thing, I think it's obvious what I mean, and it's not. That's right. Teaching, right?
So it's like 3 equal pieces of pie.
There you go. Okay, now we're talking about pie. You should have started there, because I understand that totally. Okay, all right. So the point is that we want to be specific in what we say, okay, and what we mean. So yes, you have 3 equal portions. One of them is smokers. The other 2 is non-smokers. Same.
Oh, that's important. Okay. Yes.
Could I simulate it with cards? Could I simulate with cards?
Yes.
How?
Could you maybe do like 3 red cards or 4 red cards and then 8 black cards, shuffle them and pick at random, the red being smoke?
You certainly can, but I think you pick 12 because there's 12 students, right?
Yes.
But remember, each student represents just one experiment. So I don't need 12 outcomes in my experiment to match the 12 students. I'm just going to do that. I'm just going to do this 12 times. So what's the easiest thing you can do with cards 12 times that we want a 1 in 3 chance?
Does it have something to do with, but I'm thinking 4 suits. So you have to divide it up into thirds again, the cards.
So
no?
remember, what we want, we don't have to use all the cards, right? Our opinion was correct. You don't have to use all the cards. So we just need a situation that has a 1 in 3 chance of occurring.
You can leave out like one of the diamonds and make one of the red cards mean that they do smoke, and then the other black cards to be representing that they don't smoke.
Sure, you can do that. Or how about this? Just give me 3 cards.
You can use the face cards.
I don't even need the face cards. Give me 3 cards. Ace, 2, and 3. Ace is smoke, 2 and 3 are non-smoke.
Why did you just interrupt?
Huh? Right? Just give me 3 cards. Right? 3 cards. Ace means that they smoked, and 2 and 3 means that they don't smoke. 1 in 3 chance. Right? Do I really want to shuffle 51 cards over and over and over again?
What if you don't get an ace?
Then that child that you spoke to doesn't smoke.
So would these 3 cards be randomly chosen
Well,
from the deck, or would you have to choose them? That's why I asked.
So you pick whichever 3 cards you want. So let's say you go through the deck and you say, first 3 cards you take out of the deck, you look at them, they're an ace, 2, and a 3. You're like, okay, I'm going to shuffle these cards. And if I pick an ace, that's a smoker. And if I pick a 2 or a 3, it's a non-smoker. You want to pick a jack, 7, and 5? Fine, I don't care. Just pick 3 cards, label 1 as smoker, the other 2 as non-smoker, and pick randomly. All we need is a situation with a 1 in 3 chance. And that simulates the real life situation of a 1 in 3 chance.
I'm sorry, jump ahead like 30 years from elementary school or whatever. What is a practical application of this? Like,
Okay, you want a practical application? I'll give you a practical application.
just so I understand.
I will give you a practical application. I've been teaching for 20-something years. And this past summer, or the past year, in fact, I was thinking of changing careers. And the career that I was going to do is called actuarial science. Actuarial science is basically advanced statistics for insurance companies and organizations where risk is a huge factor. And my first job as an intern this past summer was to write a program where I simulated 100,000 accidents, car accidents, using past data of the likelihood of an accident and how likely, what damages might occur and how likely that damage was, etc. And I created this program of about 400 or 500 lines of code. Do I actually want to go out and actually have 100,000 accidents to determine these likelihoods? No, I will simulate it. Okay, so I wrote a simulation. That's actually, it's called a Monte Carlo simulation. That's the name of what I did this summer. You want a practical application? Can't get any more practical than what I spent my summer doing. Okay, I'm a very popular guy, obviously. So, a lot of fun and parties that I would ever get invited to if I was. But the point is that there are certainly applications for simulations. And even in this baby case, this is a simple case of 12 students, it's a lot easier to pick a card 12 times, to roll a die 12 times, to spin something 12 times, than to go out and find 12 students. Mm-hmm. Okay, that's the whole point of simulation. It's easier. Okay, so let's scroll down now to slide number 4. Okay, slide number 4. It says class activity. Okay, it says about half of all kindergartners are girls and about half of all kindergartners are boys. Would you say this is representative of Los Angeles, California, America, the world? Would you say it seems like it's relatively representative? That half?
Somewhat.
Huh?
Somewhat.
Somewhat. I mean, I don't know the exact stats. Maybe it's not exactly half, but as a first guess, does it seem reasonable that we would start off by saying it's half? Okay. Let's say you just got your first job. You're going to be teaching kindergarten next year. You are so excited. And you're like, oh, I can't wait. I love kids. They're amazing. They're so sweet. And they never misbehave. And they follow directions. I love kids so much, right? You're an idiot who likes kids. Fine. Okay, so you're getting a kindergarten class, and your principal comes to you and says, by the way, your class is going to have 15 kids in it. And you say, cool, 15 kids. I want to start preparing what I'm going to do next year. But wait, if it's predominantly boys, I might do one thing. If it's predominantly girls, I might do something else. And if it's a good mix, then maybe I'll do something else. So you're gonna plan your curriculum based upon gender. Yeah, that's what you decided to do. But you're not sure how many boys and girls you have. So you want to create a simulation that comes up with a likelihood of having no boys, or one boy, or two boys, or 3 or 4 or 5 or 6 or 7, all the way through 15. So how are you going to create this simulation? Here's what you're going to do. You're going to take a coin and you're going to flip it 15 times. Every heads represents that there's a boy in your class, and every tails represents that it's a girl. So if I flip the coin 15 times and I get 9 heads, what does that mean? That I had 9 heads?
9 girls.
9 boys.
9 boys,
9
right?
boys.
That means that my class had 9 boys in it. I simulated my class by rolling a coin or flipping a coin 15 times, correct? Okay, now, if I only do this one time, how certain am I that that is a likely or not likely outcome? Maybe 9, it was a fluke. Maybe getting 9 boys happens 1 in a million. I don't know. If I only do it one time, I don't really have a lot of data. That just means, okay, my simulation was 9. What I want to do is I want to do this lots and lots and lots and lots and lots of times. So let's say, for example, I flipped my coin 15 times, 1,000 times. So 15 flips, result number 1. 15 flips again, result number 2. 15 flips again, result number 3. And I did this so I get 1,000 results. So how many coins am I flipping in total if I'm flipping 15 coins 1,000 times?
15,000.
15,000. That's a lot of flips. Correct? It's a lot of flips. But let's say I was really bored one day and I decided I'm going to flip a coin 15,000 times. So what I might get, if you look at this slide, the next slide, it says you have a table here. On the first line of the table are all possible outcomes for how many boys you can have, right? 0 through 15, correct? Right?
Yes.
The second line of this table is how often each of these outcomes occurred. So if I did this 1,000 times, some of those times I would get 0 boys. Some of those times I would get 1. Some of those times I would get 2 and 3 and 4. And some of those times I would get 15, correct? So I might have like 7 times I got 0, 19 times I got 1, 42 times I got 2. And when you add up all of those numbers, what would go into the box on the far right to the top total? What do all of those numbers have to add up to in my example?
15,000.
Not 15,000. Remember, 15 coins is 1 run. 15 coins, 9. I put a mark by the 9. I got 9 once. So every time I flip 15 coins, I make 1 mark on my sheet. How many marks on my sheet am I going to make altogether?
Would it be 15?
It will not be 15. So let's try this.
1,000.
It will be 1,000.
1,000, yeah.
It will be 1,000, right?
Because each flip is 15. Or each mark is 15, I should say.
Each mark is 15, right? So if I did my first, if I flipped,
You're not marking it till it's 15? And every 15th time you mark it, is that what you mean?
yes. So mark
Yes.
9, right? You flip 15, you get 9 heads. Mark the 9. You flip 15, You get 7 heads, mark the 7. You flip 15, you get 3 heads, mark the 3. So this is run number 1, this is run number 2, and this is run number 1,000. So we have 1,000 runs. And each run corresponds to 15 flips. And each time we get 15 flips, that corresponds to 1 mark. So how many marks am I going to have in total on my sheet? I'm going to have 1,000 because there's 1,000 runs. So the first line in that table is the possible outcomes, 0 through 15. The second line is going to be how many times each of them occurred, totaling 1,000. The third line is going to be the likelihood that each of them occur. Suppose out of the 1,000 times I got 0 12 times. What would I say is the likelihood that 0 occurs?
12 out of 1,000.
12 out of 1,000. And I would fill in the bottom row with all of the second row over 1,000, because that's likelihood now. And what would that row have to add up to?
15,000.
Nope.
1,000 over 1,000.
Which is 1.
1.
Right? You add up all the probabilities. It's got to be one of them. The likelihood of this plus the likelihood of this plus the likelihood of this plus the likelihood of this. You go across the board. You get 100%. It's got to be one of them. It's got to be 100%. You get 1. All right. It is 3:15, and my other class ended here as well, so I don't want to go beyond. So we'll stop here. I will see you guys on Thursday. We did finish the first chapter today. So the first homework is going to be due next Tuesday, and we will have our first quiz on chapter 1 on Tuesday. What I'm going to do over the weekends is post the solutions to the homework so that you have a few days to look them over. And then on Tuesday itself, we'll start by answering any last-minute questions that people still have, and then we'll go into the quiz immediately following. Okay, so this will give you an opportunity to see the solutions before the quiz. Sound good?
Yes.
Okay, then I will see everyone on Thursday.
You'll have more info on the quiz on Thursday, correct?
If you need more info, I will provide more info. But
I just wasn't sure if it's going to be on.
Just chapter 1.
No, on Canvas.
Oh yeah, I'm not sure about that yet. I gotta decide what I want to do about that.
Okay, cool.
Okay, now Patty, you're doing great. I'm not sure what you're doing, but you're having a good time in math class, so I can't complain. All right, so.
Professor, I have a question. As far as for me, since I'm going back to your Monday's class, do we have class on Monday?
We do not. Labor Day, unless you want to meet. That'll be great.
So what's going on with the quiz? Are we going to have it on Wednesday?
Yeah.
About next Wednesday?
Yeah, next Wednesday.
Okay. And then are you going to be able to fix my grade? Because my grade's really low because of my attendance.
Yeah, don't worry about that. I'll get around to it eventually. Don't worry. Just keep bugging me. Just keep bugging me and say, I was there and fix it, and I will eventually, and everything will be fine.
Okay. Thank you so much.
Don't worry about those grades. They're just temporary.
Okay.
Okay.
All right. Thanks. Bye.
Okay. Daisy, I'm not sure who that person is, but that's just strange.
Sorry, that was my dad. He was leaving for work.
I believe you. Okay. Any other questions? Yes, go ahead.
So I'm looking at the PowerPoint for the class activity, and I mean, I get what we were doing, but say that we don't want to do 1,000, right?
Right. So the class activity was that everyone in the class does it once, and you get something like 40 results. Right?
Oh. Okay.
But I didn't want to do 40. I want to do 1,000, so I changed the number.
Okay. So do we fill out the class activity ourselves?
Don't have to. Don't have to. I was just using it as an example. You do not have to fill out the class activity. It was just an example. Because unless we all have 15 coins, we can't really do it. If we were actually in class, then I would bring, apparatus and stuff, and we can do it quickly, but we don't. This is a scenario where it's a little more difficult, and we're already behind, so we got to catch up.
Okay. All right. Thanks.
Okay? But as long as you understand, I'm happy.
All right. Thank you, Professor.
You're welcome.
Professor, if the quiz is not on Canvas, how else would we take it?
Well, you can do it you can write it out and send me a picture via email. You can put it, you can attach it to a carrier pigeon and have it fly to me. I mean, there's various options that it can get here. We'll figure out something.
Oh, okay. No, but I was wondering, so it wouldn't be in
Smoke
person.
signals. Sorry, go ahead. What?
They don't get the carrier pigeon.
They're a little young. What can I say? So Daisy, go ahead. What?
So it wouldn't be like in person, correct?
No, it would not be in person.
Oh, okay.
No, I don't want to see anyone. No. No, I like never leaving my house. This pandemic is awesome. I get to sleep in. I don't got to drive anywhere, take naps between classes. I love this. All right. So I do admit it's a little harder to teach and to learn, but you know, what can you do? At least I don't got to spend money on gas. So there is that. Any other questions?
I had a question about the slides. I currently, since I haven't technically enrolled, I was looking at the class, the one I was taking, and the slides are completely different. Like what you're doing, like I don't have those problems.
What do you have from him?
So far we've done intro to probability. I had some of the stuff that was similar to what you were saying, but it was kind of moved around. And then when you started talking about the simulation, we didn't have that at all. We started doing rules of counting.
So rules of counting is next. That's going to be chapter 3.
Okay, because he did mention that he skipped some stuff, and I believe it might be what you're doing.
So so hopefully we'll have you into the class very, very shortly, and you can see them. But what you can also do right now is if you email me again, say, can I get the PowerPoint for chapter 2? Then I will email it to you.
Okay, perfect.
Does that sound good?
And then, yeah, and that way I can also catch up on the homework and all of that.
Yes. So ask me for 1 and 2. So I will.
Okay.
I will get you chapter 1 as well.
Okay. Thank you so much.
You're welcome, so little. All right. So, any other ones? People sticking around? Does that mean they're really not here and they're just pretending to be here? Well, not the ones who are on video, of course. But Lori, how you doing? How's class so far? She left. Okay, fine. Be like that. Wow. I asked her a question and she leaves. How rude. It's crazy. Raina, how's everything going?
Good. I just wanted to be sure. So you said that quiz is on Wednesday, right? Or Tuesday?
What, the quiz?
Yeah.
Next Tuesday.
Oh, Tuesday. I thought it was Wednesday.
Next Tuesday.
Okay.
Okay?
Got it. Thanks.
Okay, bye-bye.
Have a good day.
You too.